So we're going to talk about volumes by cross-section. So this is technically finding the volume, obviously, of a three-dimensional object, but we're going to cheat it. We're not really going to use 3 dimensions. We're only going to use 2. Three-dimensional calculus is called multivariable calculus. It's pretty interesting. It's usually the third calc class, Calc 3. But we're gonna cheat it here. We're just going to use 2 dimensions. So we're going to start off with something called a cylinder. I'm sure you're familiar with a cylinder, but when I say cylinder, you probably think of something like this, right? This is a circular cylinder. But a cylinder is really just any three-dimensional object that has parallel bases that are the same shape. So a circular cylinder has bases that are circles. Makes a can, right? But you can have any sort of three-dimensional cylinder. Oh, why? Why did I? I'm not going to be able to recreate it. You could have something like that. And there we go. There's a cylinder, right? And the volume of a cylinder in general is the area of the base. So think of the area of this times the height, where capital B is just the area of the base. So you're probably pretty familiar with a circular cylinder. The area of a circle being what? Good. So then the area of that base, pi r squared. So the total volume of the cylinder would be pi r squared h, right? That's it. So as long as you know a formula to find the area of the base, you can find the volume of any shaped cylinder. Does that make sense? All right, so let's say we want to find the volume of a three-dimensional solid, and we're going to start with an artisanal loaf of bread. So it's not a grocery store loaf, it's artisanal. It's not uniform in the size of the slices. So if we look at what's called a cross section, that's just slicing a plane perpendicular to this figure, we get a cross section. You get a single slice of bread, right? So I want to find the volume of my artisanal loaf of bread. And to do that, we're going to do something sort of familiar, similar to how we started finding area under a curve. When we first started approximating area under the curve, what did we use? Before integrals, yeah, we used rectangles, right? And so we're kind of going to do the same here. I'm going to divide up my region into subintervals, x0 to xn. Notice that when I do that, each one of these slices is technically a cylinder, right? Where it has parallel bases. So I could find the volume of any individual cylinder by doing area of the base times height. Now notice that these are kind of cylinders that are tilted onto their sides. So this is their height, right? Well, do you remember we had a name for the distance between the indices? What did we call that? Delta x. That's what I was looking for, right? Delta x. Delta x is actually the height of each one of these cylinders, right? All right. So I could approximate the volume of the whole thing by finding the volume of each little slice of bread and adding them up. Is that going to be the exact volume? No. How can I get a more precise estimate of the volume? Smaller delta x's, more slices. How can I get exact? All right, so the volume right now equals the sum of all the individual volumes. How am I finding the individual volumes? I'm doing the area of the slice at that specific index And I'm multiplying it by the height, which is delta x, right? From I equals 1 to n. But you told me that if I want exact volume, I'm going to have to use how many subintervals? I'm going to let n approach infinity. Well, what happens then to my notation here? Good. Sigma becomes an integral, right? From a to b. xi, these were individually indexed x values, but as I use more and more, they get closer and closer together to each other, right? And as I use infinitely many, it becomes just a continuous x number line, yeah? So this, instead of being a of xi, just becomes a of x, meaning the area of any arbitrary cross-section. What does delta x become? dx. Boom. Here's how you find the volume of a figure. A three-dimensional figure that has the same cross-sections. You integrate its area. Have you guys ever seen the book carving art? Where they like carve a landscape out of a book? So what I want you to think of is that one page of that book is infinitely thin. But if you stack up enough of them, you get that three-dimensional landscape. That's exactly what we're doing here. We're adding up an infinite number of infinitely thin areas. You're stacking them up until you get a volume, basically. Does that make sense? Yeah, and that's how we get our artisanal loaf of bread. Our $9 loaf of bread. Infinitely thin. Yeah, artisanal bread's expensive. It was handmade. Yeah, that's what I'm talking about. All right, so there's your fancy definition of what we just did. So here's what I want you to think about. We're laying, in this case, we're laying the three-dimensional object along the x-axis, and we're stacking it horizontally. We're stacking these thin cross-sections horizontally, which is why we're integrating with respect to x. You could do it with respect to y, then you're stacking vertically, right? Then you would integrate with respect to y, and your limits would be on the y-axis. And we will do an example of that eventually. All right, let's do this. So our formula is for any solid whose cross-sections are similar. And I mean the geometric definition of similar. What does that mean? Same shape, but different sizes, right? We can only find volumes of solids that have similar cross-sections right now. So the cross-sections have to be the same shape. One version of those is called a rotational solid. You get a rotational solid, well, by rotating. So let's take a look. We're going to look at y equals x and y equals x squared, and we're going to rotate it around the line y equals 2. So let's sketch this out. All right, so here's y equals x. It's just a straight line with slope 1. Now, y equals x squared is a parabola. I only care about this branch because they're going to intersect each other and they're going to create a closed off region. What is that point of intersection? Where does x equal x squared? At two places, 0 and 1. Good. So that's our region. It's between 0 and 1. What's this y value here? 1. I want to rotate this around y equals 2, which is going to be here. That's my axis of rotation. So what I want you to think about is that region is going to come out of the board, go around y equals 2, and back into itself. It's going to create basically a bracelet kind of situation, right? because it's going to have a hole in it here. There's going to be nothing there. And so let's just sketch it out. I'll sketch it out by reflecting it to the other side of that line. So it's going to go up here. I'm going to have a situation like that, right? While you do that, let me see. I think I have although we all agree my drawings are insanely good, I think I have a thing that can help illustrate it a little bit better. Yes. So that's just the reflection, but what you want to think about, it's coming out and then it's rotating through the board and back around. I'll draw it in. I'm going to try and pull something up to help you see sort of what's going on here. 360 all the way around. Solid of Revolution demo. That's what I want. Yeah. I mean, to be fair, Picasso could draw really well realistically. Also. Right. All right. I don't know if this is the one I want to use because I want to be able to. So that's kind of the general idea about how the rotation looks. But this isn't with a curve that we're using. That's what I was trying to say, is I want to be able to enter my own curve. So here's the curve. I'm rotating it around the x-axis. And that's sort of the figure. That one makes kind of a vase. You know. Yeah, with a hole in the bottom. Because it does, if it intersected the x-axis, then there wouldn't be that hole, right? But that's a rotation around the x-axis. Let me see if I have a different one.
Mr. Toller, we can't see it.
Oh, I'm sorry. I'll share it with you this time. It wasn't a great one anyway. This one's maybe a little bit better. Oh yeah, it'll let me. Okay, hold on. There you guys go. I want the curve. Let's just do x squared. Let's say 2. All right, the yellow segment shows a cross section, so we're rotating this around y equals 2. Let's go to 1. Way in there. All right, so this is a piece of the region that we're rotating. So if I'm rotating y equals x squared around y equals 2, there's what the cross sections look like. And then the rotation, yeah, this is still kind of a two-dimensional, but you can sort of imagine what it looks like. So here, all the way around, there we go. Does that make sense? So what are our cross sections in this case? What shape is a cross section? I'll give you a hint. It's in yellow. It's circle. Anytime you're creating a solid by rotation, the cross sections are going to be circular. Does that make sense? Now, ours isn't going to be a perfect circle because we have a region. So namely, we're rotating this region around y equals 2. So our cross-section is going to look like this. So draw in a vertical line and another vertical line here. This is called a disc or a washer. And all it is, it's basically going to be a circle with a hole cut out of it, right? Oh boy. Where this region that I'm shading is actually going to be the solid. That's going to be the area, right? So our volume formula says the volume is equal to the integral of the area of the cross section with respect to x, right? What we want is the area of a cross section. So our cross section is a disc, which is a circle with a circle cut out of it. How do you find the area of that? You find the area of both and subtract it. So I'll just say it's pi r2 squared minus pi r1 squared, right? Where I'll call r2 the radius of the bigger circle and r1 the radius of the smaller circle, yeah? All right, well, what we would like is that area as a function of x specifically. So right now I just have the general formula. So I want to think of it as a function of x. And here's how we're going to do it. What is this total distance from our axis of rotation to the x-axis? That's 2. I agree with that. Now to get to my cross section, we went out an arbitrary distance horizontally. That's x, right? Some arbitrary distance to get to our cross section. Now to get to this point, that's y, yeah? What is that? What function does that y correspond to? X squared. That's the parabola, right? This one, this point here, is on the parabola. Do you agree? Oh. That one's on the parabola. So that y value is equal to x squared, yeah? But what I want is this radius here, yeah? So how do I get that? Well, the whole thing, you told me, Olivia, is 2, yeah? And I can just subtract off this piece, which is how much? X squared. So do you agree that R2 equals 2 minus x squared? All right. R1 is the smaller radius. Same idea, except now I need to go up to this point. Well, that point corresponds to a y value on which function? So that's also a y value, but that's y equals x. So R1 is going to be what? It's going to be the whole thing, take away this red piece, right? So 2 minus x. All right, so there are my radii in terms of x, which means I can now write my area as a function of x. Isn't that just pi times R2, which is 2 minus x squared, quantity squared, minus pi times 2 minus x, quantity squared? The hard part's over. Now that we have it, we can just apply our volume formula. So volume will equal the integral from what to what? We're stacking these horizontally from what to what? Yeah, 0 to 1. The area of my cross section is pi times 2 minus x squared squared minus pi times 2 minus x quantity squared dx. And there we go. Now, if I asked you to evaluate this by hand, you could do it. You would want to factor out the pi. And then you want to multiply everything out, right? I'm not going to make you do it by hand. Let's do it in our calculator. That's x squared, sorry. Volumes should always be positive. If you end up with a negative volume, something is up. Just like areas between curves are positive. All right, let's do this in the calculator. We're going to go with a math 9. I want to integrate. I'm going to factor out pi, actually. So let me do this. Let's do pi times math 9. The function that I want is then 2 minus x squared squared minus 2 minus x squared. That's the function that I want to integrate. I factored out the pi, comma x, and I want to go from 0 to 1. There we go, 1.676, and we're done. I want to do 2 more. Let's do this one. Let's prove, did you guys know this volume formula for a sphere? Volume of a sphere is 4/3 pi r cubed. Let's prove that. So I have a diagram of a sphere. I've put it at the center, put it at the origin. It has radius r. And then you can see I've shaded a little cross section. What's a cross section of a sphere? It's a circle. What's the area of a circle? So the area of my cross section is pi times radius squared. Now, the radius of that cross section, that's not the same as this radius, right? The radius of my cross section is actually that y value, yeah, right here. So it's actually a equals pi y squared. But because I'm going to want to integrate across the x-axis, I need my area as a function of x. Well, the radius depends on this function here, right? What is that, the equation of that function? What shape is this that I'm outlining? Do you guys remember the equation of a circle? That's a parabola. X squared plus y squared equals r squared. That's only if it's not centered at 0. This is centered at 0. Now, we really only need the top half of that circle, right? So I'm going to isolate y. So y squared equals r squared minus x squared. Because the radius of the cross section depends on that function. Meaning if I take a cross section here, I have a bigger y value, and it depends on that function, right? So square root y equals root r squared minus x squared, which is just the top half of that circle, yeah? So that y value, which is our radius here, is equal to this, right? So now I can rewrite my area as area equals pi times that, which is root r squared minus x squared, quantity squared, yeah? Well, this works out kind of nice, because then that comes out to pi times r squared minus x squared, right? All right. Well, now I want the volume of the whole sphere, so let's set up the integral. Volume equals the integral from what to what? Good. Negative r to r. Or we could recognize that it's symmetric. We could go from 0 to r and then just multiply it by 2, right? 2 pi r squared minus x squared dx. All right, I'm going to factor out the pi. So that's equal to 2 pi times the integral 0 to r of r squared minus x squared dx. Now remember, r is a constant. What is the antiderivative of a constant? So in this case, r squared x, right? What's the antiderivative of x squared? So minus 1/3 x cubed, 0 to r. X is our variable, so x is what we replace with these endpoints. So we're going to plug in r for x, and then we're going to plug in 0 for x, and then we're going to subtract, right? So doing that, we get 2 pi. When I plug in r for x, I have r squared times r minus 1/3 r cubed. When I plug in 0, I'm just going to get zeros. So I just need to simplify this. 2 pi times r cubed minus 1/3 r cubed. What's r cubed minus 1/3 r cubed? 2/3 r cubed. What's 2 pi times 2/3 r cubed? 4/3 pi r cubed, aka the volume of a sphere. All right, uno más. That means one more in Spanish. Here we go. Last one. This is from an AP free response question. These are the ones where you don't need to rack your brain to try and imagine what this looks like. You just need to remember the volume is the integral of the area of a cross-section from A to B. So here we have two regions, R and S, and they give us the graphs that enclose those regions. It says the region R is the base of a solid. The base of a solid meaning the bottom of a solid. So the solid is coming out of the board. Does that make sense? And then it says each cross-section perpendicular to the x-axis. So I'm going to put an arbitrary cross-section in. Boom. If I cut into it like a slice of cake and I pull it out and lay it flat, it's telling me that it's an isosceles right triangle with one leg across the base of the solid. That means that when I pull this out, it's a right triangle. My cross section is a right triangle. Does that make sense? What does this three-dimensional solid look like? Trick question. It does not matter. It doesn't matter. Stop trying to imagine it. What are the cross sections? What shape? Triangles. Do you know how to find the area of a triangle? Then you know how to find the volume of the solid because you're just going to integrate the area. All right, but we do need to pay close attention to a couple things. They said it's an isosceles right triangle. There's only one kind of isosceles right triangle. 45, 45, 90. It also said that one leg is in the base. That means that red leg is the base. That's important because it's not the hypotenuse that's in the base, right? All right, well, that's the base. This is the base, right? Because they're the same. It's isosceles. What's the area of a triangle? Half base times height. Now, in this special case, it's actually half base squared, yeah? Because the base and the height are the same. It's just half base times base, right? Did I lose anybody? All right, great. We have the area, but we need it as a function of x. Now the base is just this distance. How do you find vertical distance between 2 points? Subtract which direction? Top minus bottom. What's this top function? So 3 minus x squared, right? So that's y equals 3 minus x squared. What's this bottom one? 2 to the x. Y equals 2 to the x. So the distance between them at any arbitrary point would just be 3 minus x squared minus 2 to the x, yeah? So the area is 1/2 quantity, 3 minus x squared minus 2 to the x, right? That's my base. That's b. And then we said, well, you should square that, correct? All right, so we're almost ready to find this volume. This is from the calculator portion, by the way. So we are going to use our calculator to integrate this, right? Yeah. No, these two are the same that have markings on them. The base and the height are the same. The reason I colored one of them red is because I had this colored red, and I just wanted to indicate what they're saying is one leg is in the base. So this distance is this, right? No, yeah, that's my fault. Sorry. That is that, and the formula for the base is just this minus this, which gives us this. And then if I want to find the area of the triangle, it's 1/2 base squared, so 1/2 that squared, right? Don't try and imagine what it looks like. It's fine. So I'll talk about that in a second, what it looks like. But like the BMO building, do you guys know what I'm talking about? The skyscraper? It's called the Dial Building.
Yeah, the one with the helicopter.
No, it's right there.
The BMO building.
It's on the corner of McDowell and Central.
The BMO building.
Yeah. That has cross sections that are rectangular, but the top of it curves. It would create basically a spine. You know what like a skateboard ramp looks like? That's like at a skate park that's kind of curved, like a bowl with a spine. The cross section is a triangle. Don't try and imagine what it looks like. It doesn't matter. Anyway, the integral of 1/2 3 minus x squared minus 2 to the x dx. Now, what I do need is the x values that I need to integrate over, a to b, which are going to be these points of intersection, right? So this is where our calculator is going to come in, because we need to figure those out. So let's enter 3 minus x squared into y1. We'll enter 2 to the x into y2. So I'm doing the top function, 3 minus x squared into y1. And I'm doing 2 to the x into y2. I'm just going to do a 10 by 10 window. All right, there we go. So what I want are those 2 points of intersection, because those are going to be my limits for integration, right? So again, your calculator can do that for you. We'll just do 5 intersect. First curve, just get close to the point of intersection. All right, again, I'm going to store this. So look, if I go to x, it has that point of intersection. I'm now going to store that in alpha a. So one more time, I now want to find that second point. Second calc, intersect is the 5th option. Just get close to the point of intersection that you're looking for. Boom, boom, boom. So that's 1. I don't really need to store that as long as we can remember 1. All right. Last, math 9. What I want to integrate is, whoops, I have the 1/2 that I'm going to factor out front, math 9. And I'm going to do y1, y1 minus y2 squared. And I'm going to do comma x, comma lower boundary I stored in a, comma upper boundary we found was just 1. I factored out the 1/2. I put that out front. And then because we entered the functions in y1 and y2 separately, you do have to do y1 minus y2. Quantity squared. There we go, 3.102.